Hello everyone, this is chapter 6.2, right triangle trigonometry. And here I first want to start off with a very generic right triangle with angle theta. Hypotenuse I'll call r, the side opposite of the angle I'll call y, and the side next to or adjacent to the angle theta I'll call x. Of course, x for horizontal, y for vertical, and r for radius. So kind of think of this sitting in a circle where this is the center of the circle, then the hypotenuse would be the radius of that circle. So that's something we kind of saw a little bit of when we saw the unit circle, and we'll basically be embedding this in the unit circle a little bit later on. But for right now, I just wanted to introduce the trig ratios. And when it comes to right triangles, there are, well, how many ways can you take ratios of sides of a right triangle? Well, any triangle has three sides. And if you wanted to take the ratio of two of those three sides, there are actually a total of 6 ways of doing it. And they have special names in this case. So I'll just start off by listing them out. So sine is opposite over hypotenuse, so that's y over r in this case. Cosine is going to be adjacent over hypotenuse, so that's x over r. Tangent is opposite over adjacent, so that's y over x. Just like that. Now these other ones are less known, but they are the so-called reciprocal trig functions. So there is cosecant, secant, and cotangent. And they're just literally the reciprocals of the ones that they sit next to. That's why I wrote them in this order. So this will be the opposite side over, well, I guess the hypotenuse over the opposite side is what I'm trying to say. There we go. Secant will be the reciprocal of cosine, which is hypotenuse over adjacent. Cotangent is then adjacent over opposite. So that's going to be x over y. Very good. Now these names are the 3-letter abbreviations for the entire name of the function. So you don't say sin, cos, and tan. You say sine, cosine, and tangent. I'm not going to spell out the name, but you can look it up and you can verify that, how you actually spell it out. Of course, this is secant, this is cosecant, and that is cotangent. So each function has a co-function. Sine has a cosine, tangent has a cotangent, and even secant has a cosecant. We'll discuss more of that later. Also, very often people remember this acronym. SOHCAHTOA, of course, stands for sine opposite over hypotenuse, which it is defined as, cosine adjacent over hypotenuse, and tangent opposite over adjacent. And now we're just going to take a look at some example here. By the way, in this section we'll be using a lot of results from geometry, so I'll just kind of mention them as they appear. One that we will be seeing right now is the Pythagorean theorem, because of course I only give you two of these three sides of the triangle. We can definitely find the third side here. If we call it b, so let's recall what Pythagorean theorem says. So the Pythagorean theorem basically says that if you have a right triangle whose side lengths are a, b, and the hypotenuse is c, then a squared plus b squared is equal to c squared. So I'll be recalling these geometry results as they appear, but I won't be proving them. The proofs of a lot of these things aren't super obvious, but they're really nice to see, so I'm super tempted to prove some of them to you. I'm not going to, it just takes too much time. But you can look up the proofs if you'd like. They're honestly a joy to look at. But anyways, so I'm going to use that here. So in this particular case, we have 5 squared plus b squared is equal to 13 squared. And that tells me that 25 plus b squared is equal to 169. If we subtract, we get b squared is equal to 169 minus 25 ends up being 144. And 144, as it turns out, is actually 12 squared, meaning that b has to be 12. Perfect. So let's rewrite this, and instead of b, I'll write 12. Good. So now in this example, I didn't actually write what I wanted you to do, but here's what I want to do. I want to actually find all of these trig functions, these trig ratios of, well, this angle theta. So namely, I want to find sine of theta, cosine of theta, tangent of theta, and then we can find the reciprocal ones, cosecant of theta, secant of theta, and finally cotangent of theta. Okay, So let me separate that from the work here. Now, sine of theta is going to be, again, opposite over hypotenuse, so it's 5 over 13. Cosine is adjacent over hypotenuse, so it's 12 over 13. And tangent is opposite over adjacent, which is 5 over 12. Perfect. Cosecant is just the reciprocal of sine. Secant is the reciprocal of cosine, and cotangent is the reciprocal of tangent. So really, these ones are just 13 over 5, 13 over 12, and 12 over, I meant to say 5 here. 12 over 5. There we go. So that's it. This is the answer for this problem. I just wanted to find all trig ratios of this angle. By the way, just so we're kind of understanding the notation here, let me just write that in this spot, I guess. So I'll just use sine as an example. But sine theta means sine of theta. So kind of think of f of x. Sine is a function. This is the name of a function. Where theta is our input. In fact, in particular, in the context of trig functions, well, theta is an angle. So the inputs of trig functions will be angles, and their outputs will just be ratios of the sides of the triangles of, well, of the triangle that contains that angle in interest. All right, now we're going to talk a little bit more about specific cases of particular angles. We'll have to, again, recall some geometry results, so let's take a look at that right now. All right, so as I said, we do need a few results from geometry, and here's one regarding special types of triangles. So if you have a perfect triangle, that is a triangle that is equilateral, all of the sides are the same, as a consequence, it's also equiangular, meaning all of its angles are the same. Also, I'm not going to actually write it down, but as it turns out, the sum of all angles of a triangle is 180 degrees. So in this case, if they're all the same angle and they add to 180, well, then they're each 180 over 3, which is 60. So each of these angles is 60. Now, another result, so it's like we're seeing all these weird results, but if we cut this in half, there's two very important things that happen. The first thing is that this line will not only be perpendicular to the base, but it'll bisect the base, so it'll cut into two equal halves, and it'll also bisect the angle, as it turns out. So with that being said, if you look at half of it, if this side is S, then now we have a right triangle. This would be now the blue side of our bisector, basically. And this side here is half of S, which is S over 2. This would be 30 degrees because it's half of the angle 60, which makes sense because, well, 90 plus 60 is 150, and 150 plus 30 would give you 180. Good. Now, where did I get this from? Well, I'm just using Pythagorean theorem. I'm not writing the actual work down, but you can verify that on your own. If you do this squared plus this squared equals this squared and solve for this one, so let's say call this b like we did in the previous example, b squared plus s over 2 all squared equals s squared. Solving for b will give you that b is equal to the square root of 2 over, well, the square root of 2 times s. Right, so now we can actually use this triangle to find particular values of our trig functions. Now, I'm not going to use the reciprocal functions here. You can verify those on your own. But I will be verifying the three main ones, sine, cosine, and tangent. So let's see. Sine of 60 would be, well, it would be opposite over hypotenuse. So notice the s's cancel and we just get radical 3 over 2. Cosine of 60, well, that's going to be s over 2 over s. Also the s's cancel and we just get 1 over 2. Let's see, tangent of 60 is going to be this over that. The s's cancel, and if you multiply top and bottom by 2, basically you're dividing by this number is multiplying by the reciprocal of this. So really when the s's cancel, the 2's also cancel. So this is really radical 3 over 1, but I'll just write it as radical 3. Good. And now we can actually find out, believe it or not, the trig functions for 30 as well. If we kind of tilt our heads here, and imagine this is our angle of interest now. Now I ask, what is sine of 30? Well, remember, sine is opposite over hypotenuse. Opposite of this angle 30 is s over 2. Dividing that by s, we already did that when we did cosine of 60. We got 1/2. Similarly, if you wanted to do cosine of 30, it would be the same result we got for sine of 60, which is, well, radical 3 over 2. Now, if you notice some pattern here, we'll actually discuss this pattern in more detail a little later. But anyways, moving on. For a tangent of 30, well, let's see. So tangent, again, is opposite over adjacent. So looking at 30, opposite of 30 is this, and adjacent to 30 is this. So notice if we divide by s, because the s's always cancel. In fact, if you let s be 1, this seems to be a little easier on the eyes. We're really doing 1 over 2 divided by radical 3 over 2. But when you divide fractions, you could just multiply the top fraction by the reciprocal of the bottom fraction. So you really just get this, the 2's cancel, and you get 1 over radical 3. Now that's fine, you could write it like that. There's another way you can write this though. You can actually multiply top and bottom by radical 3 so that there's no radical in the denominator. Now this procedure of getting rid of a radical in the denominator is called rationalizing the denominator. You can also rationalize the numerator, but very often the norm is to rationalize the denominator. So you'll see a lot of that in textbooks. So I'll also write this as radical 3 over 3. But as it turns out, these are indeed equal. And we'll be doing that here actually as well. So kind of keep that in mind, that if you were to find the reciprocals of what we just found for cosecant, secant, and cotangent for these angles, well, you would probably have to rationalize in order for it to line up with something you would see from a textbook. Otherwise, it may look a little funny. You may get something like this, right? So now, sine of 45, well, before I get there, this is a result of an isosceles triangle, kind of similar to what we saw for perfect triangles. An isosceles triangle has a nice result from geometry that if two sides are the same in a triangle, that's called isosceles, then the angles opposite those sides, the base angles in other words, are actually the same measure. So now, in particular, if we let this angle be 90 degrees, then we have a very special case, which is it's a isosceles right triangle. And an isosceles right triangle, well, since both of the angles are the same, and this angle is 90 because it's a right triangle, that means these two would have to add up to 90 in order for all three to add up to 180. So these each have to be half of 90, which is of course 45 degrees. Now also as a consequence from Pythagorean theorem though, s squared plus s squared is equal to 2s squared, and if you square root that, you get radical 2s. All right, so now I think we're good to go. By the way, there are a few things I want to point out here. This type of triangle and this type of triangle are often known by their angles in order. So this is known as a 30, 60, 90 triangle, whereas this one is of course known as a 45, 45, 90 triangle. And these are the special names for these triangles. All right. Now we can move on to find sine, cosine, and tangent. So let's see. Sine of 45, no matter which one you pick, here there were different angles. If we looked at 60 or looked at 30, but here they're the same. So we only get one set of results here. So sine of 45 is going to be s over radical 2s. The s is canceled, so we get 1 over radical 2. Same thing goes for cosine actually, because, well, opposite is equal to adjacent in this case, so we get also 1 over radical 2. And for tangent, well, tangent again is opposite over adjacent, so we get s over s, which is actually just 1. Now, yes, we can rationalize sine and cosine, but they're both the same result. So if you multiply top and bottom by radical 2, you get radical 2 over 2. There we go. Now, one thing I want to say before moving on is that, remember that 60 degrees is equal to pi over 3 radians. 30 degrees is equal to pi over 6 radians. So keep that in mind. Also here, for this particular set, well, 45 degrees is equal to how many radians? Pi over 4 radians. So keep that in mind. So we'll often be using radians here. Also, if you try to find sine and cosine with your calculator and see that you get these values, you need to make sure that you're in the correct mode. And that depends on each calculator. For the TI-83 Plus, for example, if you just press mode, go down to the third option, there will be either radians or degrees, highlight which one you want, and then if you, let's say, pick degrees, type in sine of 45, you'll get, well, 0.707, which is actually radical 2 over 2 if you evaluate that correctly. But if you are in radians, you won't get that. But the good news there is if you're in radians, don't ask your calculator what sine of 45 is. Ask your calculator what sine of pi over 4 is. And then you'll get 0.707. So now moving on to the next idea. All right, so now I'll discuss some fundamental identities. By the way, the word identity just means basically an equation that's always true. So here we'll have these equations that are always true no matter what theta is. So in fact, we can play around with these identities to actually find some pretty cool results and also answer some kind of challenging questions that otherwise without the identities would be kind of difficult to do. And I'll try to justify them the best I can with this image here, but anyways, moving on. The cofunction identities here basically give us insight as far as why they're named what they're named. So a cofunction of a trig function would just be when the argument, in other words, the input, is 90 degrees minus the angle. So sine of 90 minus the angle is cosine, secant of 90 minus the angle is cosecant, and tangent of 90 minus its angle is cotangent of that angle. Now, why is that true? Well, remember that all angles in a triangle add to 180, so if this is already 90, what does theta have to add to result in the other 90 so that the total will add up to 180? Well, it would have to be 90 degrees minus theta. Because notice when you add these together, the thetas cancel, you get 90 degrees. So these pairs will always add to 90 in a right triangle, that's true. And then adding that to this right angle 90, you get your 180. Perfect. Now, well, if we kind of compare, what is sine of 90 minus theta? Sine of 90 minus theta is opposite over hypotenuse, which is the same as adjacent over hypotenuse of the other paired angle theta. So there we go. And you can kind of verify the other ones for yourself, but I'm just going to move on from here. Now for reciprocal identities, these ones are pretty straightforward. They're based on the definition of cosecant, secant, and cotangent. They're the reciprocals of the definitions of sine, cosine, and tangent, respectively. So cosecant is 1 over sine, secant is 1 over cosine, and cotangent is 1 over tangent. The same actually goes for the other way around. So sine is the reciprocal of cosecant because, well, reciprocals are reciprocals of each other. Also, if you just think of swapping these two by multiplying both sides by sine and dividing both sides by cosecant, you get this. Same can be said with these other two. And finally, we see the quotient identities here. These aren't actually too hard to verify. Notice the tangent is y over x in this case. Sine would be y over r, and cosine would be x over r. So with that being said, if you actually write it out, I'll do it for you. So for sine is y over, let's write it like this. Sine is y over r over cosine is x over r. If you multiply top and bottom of this fraction by r, the r's cancel and you get y over x, which is indeed tangent. And then from there, the next one becomes super obvious because since cotangent is just a reciprocal of tangent, all we need to do is reciprocate this and we'll get the cotangent quotient identity. So there's one more fundamental identity and it's probably the most important. I wanted to leave space for it so I can talk more about why they're true. There are 3 of them that are called the Pythagorean identities, and let's take a look at those right now. So here are the Pythagorean identities. They're sine squared plus cosine squared is equal to 1, and the rest actually follow from this. So just to justify them, I'll do this. I'll kind of refer to this and let's think of, well, first off, they're called Pythagorean identities, of course, because they derive directly from Pythagorean theorem. So, well, let's just kind of consider what cosine squared and sine squared are. By the way, the notation here is the following. So let me just say, using sine again as an example, sine squared theta means sine of theta all squared. So that's just a notation we're using just so we don't write too many parentheses. In fact, if you think about it, there are technically parentheses here using the function notation. So you kind of see that the notation is just in favor of writing less. So as long as we understand what they mean, there's no issue. All right, so what is sine squared? In this case, sine squared is going to be, well, sine is y over r. So y over r all squared, that's sine squared of the angle theta. Plus, what is cosine squared? Well, cosine is x over r. So this is going to be x over r all squared, and that is cosine squared. And this is supposedly equal to 1, but if we use Pythagorean theorem, well, kind of think for a second. a fraction squared is just squaring the top and bottom. So this is actually the same as, let me write it over here. This is the same as y squared over r squared plus x squared over r squared. Now, since they both have the same denominator, we can write this legitimately as y squared plus x squared all over r squared. But what does the Pythagorean theorem tell you in this particular triangle? It tells you x squared plus y squared is equal to what? R squared. So that means this numerator y squared plus x squared is just r squared. So this whole fraction is really just r squared over r squared, which is always 1. So great. So that justifies the first Pythagorean identity. So no matter what the angle is, as long as they both have the same angle, then the result is 1. Now, to justify the other ones, you could actually justify it in a very similar fashion that I did this, but there's a better way. And the better way is to just divide through by sine squared or cosine squared to make one of these a 1. So if you divide through by cosine squared, that'll make this a 1. Notice since sine over cosine is tangent, sine squared over cosine squared will be tangent squared. Also for this term, dividing this by cosine squared, well, 1 over cosine is secant, so 1 over cosine squared is secant squared. Similarly, if you divide everything by sine squared, you'll get this third Pythagorean identity. So it's kind of nice. You could try that on your own, and it works out really, really nicely. So I recommend you all take your time to try and do that. And now this example here asks us to find all of the remaining trig ratios of this angle theta, given only one of them. And that's a pretty common example, to be quite honest. Of course, we have to be given that the angle is acute, meaning in between 0 and 90. And in right triangle in trigonometry, the angle is always acute. In fact, we'll see in later sections how we can take trig functions of an angle that is beyond 90 degrees or even equal to 90 degrees. But as of right now, we can't do that. That's just, me kind of rambling. But anyways, let's see if we can find something else. Well, of course, cotangent's a freebie. Let me just kind of write out a list here. So I'm going to write here sine, cosine, tangent. That one we know, that's 4 over 5, so that's good. Cosecant, we don't know. Secant, we don't know. And cotangent, well, cotangent we know. Cotangent is the reciprocal of tangent, which is 5 over 4. So we'll see, hopefully, good use of all of the identities we've seen so far. Maybe with the exception of the cofunction identities, because these are all theta, not 90 minus theta. Well, anyways, so how do we get from tangent to one of these? Well, the only identity here that involves tangent is the second one. So let's see if we can make some headway with that. So according to this, tangent squared, which is 4 over 5 in this case, so that's squared, plus 1 must be equal to secant squared. Perfect. So let's see, 4 over 5 squared is 16 over 25. Since 1 is 1 over 1, you can write it as 25 over 25. Perfect. That's secant squared. They're both over 25, so now all we need to do really is just add the numerators. 16 plus 25 is 41. That's secant squared. So that means if you square root, you get secant, which is the square root of 41, over the square root of 25, which is just 5. And it's already rationalized for us, so that's great. So now we know secant is radical 41 all over 5. Perfect. And even better, we can actually find cosine from this because, well, the reciprocal of secant is cosine and vice versa. So really what I want to write for cosine is 5 over radical 41. But just so we're rationalized, well, let's multiply top and bottom by radical 41. The square root of 41, as it turns out, doesn't really simplify at all. So really what we get here, let me just write the result over here, is 5 radical 41 divided by 41. Perfect. And there are a few ways we can continue. We actually could do the same thing we did for tangent, from tangent to get to cosecant, and go from cosine to get sine using the first Pythagorean identity. And if you want, you can try that on your own that way. Instead, what I'm going to do is the following. I'm going to say that tangent, which is 4 over 5, is equal to sine over cosine. And we know what cosine is. Cosine is 5 radical 41 over 41. So to find sine, all we have to do is multiply both sides by this denominator. So multiplying both sides by 5 radical 41 over 41, notice what happens here. The 5's cancel, so we actually just get these cancel. So we just get that sine is equal to 4 radical 41 over 41. So it's 4 radical 41 over 4. So pretty disgusting numbers, to be quite honest. But, oh, and the reciprocal of that. Well, let's see. If we reciprocate this, we'll get 4. Let me write it over here. We'll get 41 over 4 radical 41. If we multiply top and bottom by radical 41 to rationalize the denominator, notice in the denominator, radical 41 times radical 41 is just 41 itself, which cancels with this. So really, we just get radical 41 over 4. Anyways, like I was saying, these are pretty gross numbers. I'll just box this. But that's kind of what we open ourselves up to when we use the Pythagorean identities, because since there are squares involved, you imagine you'll get square roots. In fact, it's very rare that you have no square roots in these types of questions. It's possible, but they're rare. So just kind of keep that in mind. Since we'll be using these, square roots will emerge. Even if you don't use these, there's really no other way of doing it. I'm just kind of trying to say that expect to see square roots in pretty outrageous numbers like this. Probably worse than this, to be honest, in general. Anyways, now let's take a look finally at an application problem, which I think you'll all enjoy. So for this particular problem, like I mentioned, it's an application problem. There's this cell tower that's, standing up from the ground, and it is connected to this support wire, which is called a guy wire. And the angle is given, the height of the tower is given, but these two lengths are not given. So part A here asks us to find the length of the guy wire, and part B asks us to find this distance here, the distance from the base of the tower to where the guy wire is anchored to the ground. So it wouldn't be a bad idea here to label these things. Let me call this distance, I guess, x, and this distance r, kind of like our usual notations, usual labelings. And of course, here we have a unit feet, so they'll both be in feet then. So just kind of worry about the number for right now, and then we're good to go. So let's just take a look at what we have. So we have an angle with a specific number, a specific value, and we can get trig functions involved. Now, the thing we haven't really done yet is use our calculator to find sine, cosine, and tangent of angles. We used, results from geometry to find particular values for particular angles, and there were nice exact values. But here, we're not going to care about being nice, we're just going to approximate. So in other words, we're not going to really be using radicals, we'll just be using decimal approximations, and that's fine. So let's see. Just so we can get started, let's consider sine. So what is sine of the angle? First off, the angle is 43. So what is sine of 43? Well, according to this, sine of the angle, sine is opposite over hypotenuse. So this is 150 over r. So this will help us find r, and, A is asking us to find r, actually. So how do we find r? Well, we can multiply both sides by r and divide both sides by sine of 43. Really, doing this simultaneously is known as a swap. So if you swap the denominator with the opposite numerator, what you end up getting is the following. You get that r is equal to 150 over sine of 43 degrees. Now, if you just type this in your calculator, as long as you are in degree mode, you will get about 219.9. So r is about 219.9, and that's of course in feet. Now I'm rounding to the tens place, doesn't say what place to round to, but if I were actually working on the field and doing this, I mean, it kind of seems like tens place is an appropriate approximation. Otherwise, if you wanted to round more, you could. It's really 0.94 if you round. Now moving on to part B. So this is part A. So part B is finding the remaining side x. And there are a few ways we can go about this now that we know what r is. In fact, we could use cosine. Cosine is x over r. Initially, we didn't know r, but now we do. But just to play it safe, I'm not going to do that. I'm going to use tangent because that will involve x and the side that's given. So tangent of the angle 43 would be equal to 150 over x. That makes sense. Opposite over adjacent. Good. And now doing our swap, seems like we'll probably love that now, is just x equals 150 over tangent of 43 degrees. And if you plug this into your calculator, similar to how we did part A, you will get about 160.9 actually. So it was 0.85, but it rounds to 9 if you round to the tens place. So that's what x is. And yeah, that really does it for this example. And that's actually really all I wanted to speak of when it comes to chapter 6.2. It was a lot. It was really a lot that we spoke about in this video. A lot of fundamentals were discussed here. So I wouldn't be too surprised if a few people re-watched some parts of this video just to get more insight and a better understanding as far as how trig functions and trig ratios behave. So, well, there you go. You have that now. And I'll see you in the next video for 6.3. Thanks for watching.